What is time? Hello, and welcome back to Sleepy History and Mysteries channel. Tonight, we're going to explore one of the most fundamental mysteries that has puzzled humanity since we first gazed up at the stars and wondered about our place in existence. We're going to talk about time. Not the time on your clock or the appointments in your calendar, but something much deeper and stranger. We're going to ask what might be the most deceptively simple question in all of science. What is time, really? Before we begin this gentle journey through physics, philosophy, and human understanding, take a moment to settle in. Get comfortable. Let your breathing slow. There's nowhere you need to be right now except here, learning something interesting before you drift off to sleep. The question that everyone asks but no one can answer: picture yourself standing in your kitchen, watching steam rise from a cup of tea. The steam curls upward, dispersing into the air, the tea slowly cooling. Now try to imagine that process in reverse. Imagine the scattered molecules of steam suddenly gathering themselves back together, condensing into visible wisps, and flowing back down into the cup, heating the tea as they go. It feels wrong, doesn't it? Impossible, even. But why? The ancient Greek philosopher Augustine of Hippo captured this mystery beautifully in the 4th century. He wrote, "What then is time? If no one asks me, I know. If I wish to explain it to one that asketh, I know not." Nearly 1700 years later, despite all our scientific progress, his words still resonate. We use time constantly. We measure it with extraordinary precision. We base our entire civilization on it. And yet, when we try to explain what it actually is, we find ourselves struggling with the same fundamental confusion that Augustine felt. Think about your own experience of time for a moment. You have memories of this morning, perhaps of yesterday, of childhood events that happened decades ago. These memories feel real to you, stored somehow in your brain. But are those past moments still real somewhere, or have they simply ceased to exist? And what about tomorrow morning? Or next year? Do those moments exist already, somewhere, just waiting for you to arrive at them? Or are they genuinely not yet real, to be created as the universe unfolds moment by moment? These aren't just abstract philosophical questions. They cut to the heart of what we mean when we talk about time. And surprisingly, modern physics has made these questions more difficult, not easier. The 20th century gave us Einstein's theories of relativity, which fundamentally changed how we understand time. These theories work magnificently well at predicting how the universe behaves, but they also tell us things about time that seem to contradict our everyday experience in the most unsettling ways. According to Einstein's special relativity, time is not a universal river carrying all of us along at the same rate. Instead, time passes at different rates for different observers, depending on how they're moving relative to each other. If you could travel at nearly the speed of light and then return to Earth, you might find that only a few years had passed for you, while decades or centuries had passed for everyone else. So we have this strange situation where time is both the most familiar aspect of our experience and one of the most mysterious concepts in physics. We're going to spend the next couple of hours gently unpacking this mystery, looking at it from different angles, seeing what various brilliant minds throughout history have discovered about it. How humans first measured the invisible long before anyone wondered about the deep nature of time. Humans needed practical ways to measure it. Our ancestors looked up at the sky and saw natural cycles. The sun rose and set with beautiful regularity. The moon waxed and waned through its phases. The stars wheeled overhead in their slow, eternal dance. These celestial movements became humanity's first clocks. The earliest civilizations we know of, in Mesopotamia and Egypt around 5,000 to 6,000 years ago, developed calendars and timekeeping methods. As societies became more complex, with agriculture, trade, and organized religion, people needed to coordinate their activities. When should we plant the crops? When do we hold the festival? These questions required answers, and answers required measuring time. The ancient Egyptians were particularly ingenious. Around 1500 years before the Common Era, they created shadow clocks, sometimes called sundials, that tracked time using the sun's movement across the sky. One Egyptian shadow clock design consists of a long flat piece with a raised crossbar at one end. In the morning, you would orient it east to west, with the crossbar facing east. As the sun rose and climbed higher, it would cast a shadow from the crossbar onto the flat surface, which had marks dividing the shadow into different periods. But sundials have an obvious limitation. They only work when the sun shines. What about cloudy days? What about night? The Egyptians and other ancient peoples developed another ingenious solution called the water clock or clepsydra. The basic principle is beautifully simple. You have a container filled with water, and you let the water leak out at a steady, controlled rate through a small hole at the bottom. As the water level drops, you can see how much time has passed by which mark the water level has reached. The challenge with water clocks is that water doesn't actually flow out at a perfectly constant rate. The pressure of the water decreases as the container empties, which means the water flows out more slowly as time goes on. Ancient engineers understood this problem and developed various solutions. One approach was to make the container cone-shaped rather than cylindrical. As the water level dropped, there was less water above the hole, so less pressure, but also a narrower container at that height. These two effects could be balanced to keep the flow rate reasonably constant. The ancient Greeks and Romans took water clock technology to impressive heights. In the 1st century before the Common Era, a Greek astronomer named Andronikos supervised the construction of an octagonal marble tower in Athens called the Tower of the Winds. This remarkable structure, which still stands, contained a 24-hour water clock mechanism, along with sundials on the outside walls. What's fascinating about all these ancient timekeeping devices is what they reveal about how people thought about time. Time was something external, something that could be read from the natural world. The sun's position, the flow of water, These were the things that told you what time it was. The idea that time might be something more abstract, something that exists independent of physical processes, that's a much more modern conception. Ancient timekeeping was also surprisingly relative. The Romans, for instance, divided both day and night into 12 hours each. But because the length of daylight changes with the seasons, a Roman hour was longer in summer than in winter. At Mediterranean latitudes, a daylight hour might be about 4 to 5 minutes long in winter and 7 to 5 minutes long in summer. Time, for them, was simply a way of dividing the available daylight and darkness into useful portions. It wasn't until the development of mechanical clocks in medieval Europe that hours became standardized as fixed periods of time, independent of the season or the length of daylight. This change in timekeeping technology actually changed how people thought about time itself. Time became something more abstract, more mathematical, more divorced from the daily cycle of the sun. The clockwork universe and Newton's absolute time. For thousands of years, humans measured time using the natural cycles around them. But measuring time and understanding what time is are two different things. The first person to really grapple with time as a fundamental concept in physics was Isaac Newton, and his ideas shaped how we think about time for centuries. Newton lived in the 17th century, a time of scientific revolution. He developed the laws of motion and universal gravitation, creating a mathematical framework that could explain everything from falling apples to planetary orbits. But to make his physics work, Newton needed to define certain fundamental concepts, and time was one of them. In his masterwork, Principia Mathematica, published in 1687, Newton distinguished between what he called relative, apparent, and common time, and absolute, true, and mathematical time. Relative time is what we measure with clocks and calendars. But Newton argued that beneath this, there exists something more fundamental. He wrote that absolute time flows equably without relation to anything external. Think about what this means. Newton is saying that there's a true time, a cosmic time, that flows at a constant rate everywhere in the universe, completely independent of what's happening. Whether there are planets moving or stationary, whether there's matter or empty space, this absolute time just keeps flowing, like an invisible river carrying all events along. In Newton's universe, time is like a stage on which the events of the universe play out. The stage exists independently of the play. Time would keep flowing even if there were no matter, no motion, nothing happening at all. Everyone, everywhere in the universe, shares the same time. If an event happens at a certain moment, that moment is the same for every observer, no matter where they are or how they're moving. This Newtonian view of time had tremendous practical success. Engineers could use it to design machines. Astronomers could predict planetary positions years in advance. The Industrial Revolution was built, quite literally, on Newtonian mechanics. When people in the 18th and 19th centuries thought about time, they thought about it in Newton's terms, as this absolute, universal, steadily flowing quantity. But even in Newton's time, there were philosophers who questioned this view. Newton's contemporary, the German philosopher Gottfried Wilhelm Leibniz, argued that time and space aren't independent entities but rather relationships between events and objects. In Leibniz's view, time is nothing more than the order in which things happened. There's no absolute time underlying everything. There's just events and their relationships. The practical success of Newtonian physics meant that most scientists didn't worry too much about these philosophical questions. Absolute time worked perfectly well for calculating orbits and trajectories, for building bridges and steam engines. Time was simply what clocks measure, and clocks could be built to measure it with increasing precision. Yet even as this precision increased, puzzles began to emerge in physics that would eventually overturn Newton's absolute time. Scientists studying light and electricity discovered strange things. Light always seemed to travel at the same speed, regardless of whether the source was moving or stationary. This didn't make sense in Newtonian physics. In 1887, two American physicists, Albert Michelson and Edward Morley, performed an experiment that would become famous. They tried to measure the Earth's motion through what physicists at the time called the luminiferous ether, the substance they thought light waves traveled through. The experiment was beautifully designed and extraordinarily precise. And it found nothing. No matter which direction they measured, light traveled at the same speed. The puzzle of light's constant speed seemed like a technical problem that would eventually be cleared up. No one imagined that it would lead to a complete revolution in our understanding of time itself. But that's exactly what happened, and the person who made that revolution was a young patent clerk in Switzerland named Albert Einstein. Einstein's revolution and the flexibility of time in 1905. A 26-year-old Albert Einstein was working at the Swiss Patent Office in Bern, evaluating patent applications during the day and thinking about physics in his spare time. That year, he published 4 papers that would transform physics. One of them introduced what we now call special relativity. This paper overthrew Newton's absolute time and replaced it with something far more interesting. Einstein started from a simple principle. The laws of physics should be the same for all observers moving at constant velocities relative to each other. This principle itself wasn't new. But Einstein added a second principle. The speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. These two principles seem innocent enough, but together they have revolutionary consequences. Imagine you're on a train moving past a station at high speed. You shine a flashlight forward. You measure the speed of the light and find it's about 300,000 kilometers per second. Now imagine someone standing on the platform, watching your train go by. They also measure the speed of light from your flashlight. According to Einstein, they measure exactly the same speed as you do. This seems impossible. How can you both measure the same speed for the light when you're moving relative to each other? The only way this can work is if something else adjusts to compensate. And that something, Einstein realized, is time itself. Time, according to special relativity, is not absolute. It doesn't flow at the same rate for everyone. Instead, time passes more slowly for objects that are moving relative to you. This effect is called time dilation. At everyday speeds, this factor is incredibly close to 1. At highway speeds, the time difference is a few nanoseconds per hour, far too small to notice. But at speeds close to the speed of light, the effect becomes dramatic. Imagine a spaceship traveling at 90% the speed of light. Time on the ship would pass at only about 44% the rate of time on Earth. If the ship traveled for what seemed like 1 year to the astronauts aboard, over 2 years would have passed on Earth. This isn't science fiction. We've measured it. Particles called muons, created high in the atmosphere by cosmic rays, travel at 98% the speed of light. In their own reference frame, muons only live for about 2 microseconds before decaying. At that speed, they should only travel about 600 meters. But they're created about 15 kilometers up, and many of them reach the ground. How? Because from our reference frame, their time is dilated. They live much longer from our perspective than they do in their own frame of reference. But it gets stranger. Not only does time slow down for moving objects, but the very concept of simultaneous becomes relative. In Newton's physics, if 2 events happen at the same moment, they happen at the same moment for all observers. But in Einstein's physics, this isn't true. Events that happen at the same time according to one observer happen at different times according to another observer moving relative to the first. There is no universal now stretching across space. Your now is different from someone else's now if you're moving relative to each other. Einstein's former teacher, Hermann Minkowski, made this even clearer in 1908 when he reformulated special relativity in terms of space-time. Minkowski showed that space and time aren't separate entities but are unified into a 4-dimensional continuum. Events don't happen at a particular place at a particular time. Instead, they happen at particular points in space-time. In this view, the universe is a 4-dimensional space-time, and your life is a path through this space-time called a world line. The present moment isn't a universal slice through space-time. Instead, what counts as now depends on your motion through space-time. This picture leads to what's called the block universe view. If we accept Minkowski's space-time view seriously, then all of space-time exists. Past, present, and future are all equally real, just different regions of the 4-dimensional space-time block. The flow of time, the sense that the present moment is somehow special, becomes something that needs explaining. Einstein himself seemed to lean toward this view. When his lifelong friend Michel Besso died, Einstein wrote to Besso's family saying, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." And we haven't even gotten to general relativity yet, where Einstein showed that gravity itself is a curvature of space-time, and that time passes at different rates depending on how deep you are in a gravitational field. Near a massive object like a black hole, Time slows down dramatically compared to time far away. We use these relativistic effects every day. The GPS satellites orbiting Earth contain atomic clocks synchronized with clocks on the ground. But the satellites are moving at high speeds and they're in a weaker gravitational field. Both effects change how fast time passes for the satellites. If the GPS system didn't account for relativity, the position errors would accumulate at about 10 kilometers per day. So Einstein overthrew Newton's absolute time and replaced it with something far more flexible and strange. Time is relative, not absolute. It passes at different rates for different observers. Simultaneity is relative. The present moment is not universal but depends on your reference frame. The arrow of time and entropy's one-way street. Einstein's relativity showed us that time is more flexible than Newton imagined. But it didn't really address something else that seems fundamental about time: its directionality. Time has an arrow. It points from past to future, and not the other way around. We remember yesterday but not tomorrow. Eggs break but don't spontaneously unbreak. Why? Here's the puzzle. The fundamental laws of physics don't care about the direction of time. If you film any basic physical process at the microscopic level and play it backward, you'd see something that's perfectly allowed by the laws of physics. Take two billiard balls colliding. The backward version obeys all the same laws as the forward version. Yet at the macroscopic level, in the everyday world we experience, there clearly is an arrow. Time moves from past to future. Certain things happen in one direction and never in reverse. How do we get from time-symmetric microscopic physics to time-asymmetric macroscopic experience? The answer lies in a concept called entropy, developed in the 19th century as part of thermodynamics. The second law of thermodynamics says that in an isolated system, entropy tends to increase over time. But what is entropy? A better way to think about it is in terms of probability and the number of possible microscopic arrangements. Imagine a box divided in half, with all the air molecules initially on one side. This is a highly ordered state with low entropy. Now remove the divider. The molecules spread out and soon fill the whole box evenly. This is a disordered state with high entropy. Why does this happen? It's not that any law prevents the molecules from staying on one side. It's just extraordinarily unlikely. There are vastly more ways to arrange the molecules so they're spread throughout the box than there are ways to arrange them so they're all on one side. When the molecules bounce around randomly, they naturally evolve toward the more probable state, which is the more disordered, higher entropy state. The Austrian physicist Ludwig Boltzmann showed that entropy is a measure of the number of microscopic arrangements that correspond to a given macroscopic state. High entropy means many possible microscopic arrangements. Low entropy means few. And the second law becomes a statistical statement. Systems evolve towards states with more possible arrangements because those states are more probable. This is why we see certain processes happen in only one direction. When you break an egg, you're taking something in a very special, low entropy state and transforming it into a high entropy state with everything mixed together. There are vastly more ways for the broken eggs molecules to be arranged than for the unbroken eggs molecules. Could a broken egg spontaneously reassemble? In principle, yes. If all the molecules happen to move in just the right way, the egg could reconstitute itself. But the probability is so small that even if you waited many times the current age of the universe, you wouldn't see it happen. So entropy increase gives time its arrow. We can define the future as the direction in which entropy increases. The past is the low entropy direction. But this raises a new question. Why was the entropy of the universe so low in the past? The early universe, according to the Big Bang Theory, was in an incredibly low entropy state. Matter and energy were distributed very smoothly and uniformly. As the universe evolved, that smooth distribution became clumpy. Stars formed, then galaxies, then black holes. Entropy increased, and it's still increasing today. The arrow of time, the direction from past to future, is fundamentally the direction of increasing entropy. We remember the past and not the future because memory formation is an entropy-increasing process. We can predict the future but not reconstruct the past because we use the low-entropy initial state of the universe. We see causes leading to effects, not effects leading to causes, because the causal structure is built on entropy increase. Boltzmann worked out this statistical interpretation of entropy in the late 1800s. His life is a poignant story. He defended his ideas vigorously, but he struggled with depression and professional opposition. Many prominent physicists didn't believe in atoms. In 1906, he died by suicide. The tragedy is compounded by timing. Just a few years after his death, experiments confirmed the existence of atoms. Boltzmann was right all along. Today, his equation, S equals K times the logarithm of W, is carved on his tombstone in Vienna. It's one of the most important equations in physics, connecting the microscopic and macroscopic worlds, explaining the arrow of time itself. Quantum mechanics and time's deepest mysteries. If relativity made time strange, quantum mechanics makes it almost incomprehensible. Quantum mechanics describes how matter and energy behave at the smallest scales, and it challenges many of our intuitions about reality, including our understanding of time. At the quantum level, particles don't have definite properties until they're measured. An electron doesn't have a specific position until you observe it. Before measurement, it exists in a superposition, a strange quantum state where it's in multiple places at once. The act of measurement collapses this superposition into a single, definite state. This is famously illustrated by Schrödinger's cat thought experiment. A cat is placed in a sealed box with a quantum device that has a 50% chance of releasing poison. Until you open the box, quantum mechanics says the cat is in a superposition of being both alive and dead. Only when you observe does the cat become definitely one or the other. What does this have to do with time? The problem is that the quantum measurement process seems to be fundamentally time asymmetric. Before measurement, the quantum system evolves smoothly according to the Schrödinger equation. This evolution is time reversible, but measurement causes a discontinuous, irreversible collapse. This collapse has a direction in time. Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation accepts measurement collapse as fundamental. The many worlds interpretation gets rid of collapse altogether. In this view, all possible outcomes actually happen, each in a different branch of the universe. When you measure the electron's position, the universe splits. There's no collapse, just branching. There's also a deep connection between quantum mechanics and time involving something called Kaplan symmetry. The Kaplan theorem says that any quantum field theory must be symmetric under the combined operation of charge conjugation, parity, and time reversal. This symmetry seems exact and fundamental, but individually, each symmetry can be violated. Parity violation was discovered in 1956. And in the past few decades, physicists have found evidence of small violations of time reversal symmetry in certain particle interactions. These violations are tiny but real. At the most fundamental level, the universe has a slight preference for one direction of time over the other. Quantum mechanics also raises questions about determinism. In classical physics, the future is determined by the present. But quantum mechanics introduces fundamental randomness. When a quantum superposition collapses, the outcome is random, governed only by probabilities. Even with perfect knowledge of the current state, you can't predict with certainty what will happen next. This has implications for time and causality. In quantum mechanics, the future is not determined by the past, not even in principle. There's genuine openness in how events unfold. The experience of time and the mystery of consciousness. We've explored time from the perspective of physics, but there's another aspect to consider: our subjective experience of time. Physics tells us that time might not even flow in the fundamental sense. Yet our conscious experience of time feels entirely real and immediate. You experience this moment as now. You remember the past but not the future. You feel time flowing from one moment to the next. This subjective experience is one of the deepest mysteries in philosophy and neuroscience. The philosopher William James talked about the specious present, the idea that our experience of now isn't an infinitesimal instant but a short duration, perhaps a few seconds long. When you listen to a melody, you don't experience individual notes in isolation. You experience a pattern unfolding over time. Our brains are constantly constructing this sense of the present moment from sensory input arriving at slightly different times. Light reaches your eyes nearly instantaneously. Sound takes longer, traveling at about 340 meters per second. Yet you experience all these inputs as synchronized, as happening now. This synchronization is an active process. Your brain adjusts and calibrates to create a coherent temporal experience. There are fascinating illusions that reveal this. In the flashlag effect, a moving object's flash appears ahead of where it actually was. Your brain predicts where moving objects will be, compensating for neural delays. But why does this narrative have a direction? Why do we experience time as flowing from past to future? This connects back to the thermodynamic arrow of time. Memory formation is an entropy-increasing process. Your brain encodes information about the past by creating physical changes that correlate with past events. You can't create memories of the future because the future hasn't happened yet. The physicist Sean Carroll has argued that this is why we perceive time as flowing. Our consciousness is built on memory and cognition, processes that rely on encoding information about the past. We're stuck in a universe where entropy is increasing, where causes precede effects. Our subjective experience of temporal flow emerges from living in such a universe. But this raises a puzzle. If the block universe view is correct, if all of space-time exists and the distinction between past, present, and future is illusory, why do we have this stubborn sense of being located at a particular moment? Some philosophers argue that this shows the block universe view must be wrong. The flow of time is too fundamental to be illusory. Others embrace the block universe and argue that our sense of temporal flow is a feature of how conscious beings are embedded in space-time. Neuroscience has made progress in understanding how the brain processes time. There's no single clock in the brain. Instead, timing is distributed across many regions. Some neurons act as oscillators. Others show sensitivity to timing and sequence. The cerebellum plays a role in timing movements. The hippocampus encodes not just what happened, but when it happened. Our sense of time is also highly subjective. Time seems to pass more slowly when we're bored and more quickly when we're engaged. Retrospectively, the pattern reverses. A vacation filled with new experiences feels longer in memory than the same duration spent in routine, because novel experiences create more memories. Time, in human experience, is never just an abstract physical parameter. It's the fabric of our lives, the medium in which our stories unfold. Time in extreme environments, black holes and the Big Bang. To really test our understanding of time, we need to look at extreme environments. Two of the most extreme are black holes and the Big Bang itself. Black holes are regions of space-time where gravity is so intense that nothing can escape from inside the event horizon. Einstein's general relativity predicts them, and we now have extensive observational evidence. We've detected gravitational waves from colliding black holes. We've imaged the shadow of the supermassive black hole at the center of galaxy M87. As you approach a black hole, time slows down from the perspective of someone far away. If you were watching someone fall toward a black hole, you would see them move slower and slower until they seem to freeze at the event horizon. From the perspective of the falling person, nothing special happens at the horizon. They cross it in a finite amount of their own time. What happens at the center is even stranger. General relativity predicts a singularity, a point of infinite density where space-time curvature becomes infinite. At the singularity, the equations break down. Time itself might come to an end there, or transform into something we don't understand. Near the singularity, the roles of time and space actually swap. Inside the event horizon, moving forward in time necessarily means moving toward the singularity, just as outside, moving forward in time means moving toward the future. But physicists don't really believe in singularities. They think singularities are places where our current theories break down, where we need quantum gravity to properly describe what happens. Stephen Hawking discovered in the 1970s that black holes aren't perfectly black. They emit radiation due to quantum effects near the event horizon. This radiation causes black holes to slowly evaporate. The problem is that this radiation seems thermal and random, not carrying information about what fell in. This creates the black hole information paradox. Now let's consider the Big Bang. According to modern cosmology, the universe began about 13.8 billion years ago in an incredibly hot, dense state and has been expanding ever since. General relativity, when applied to the universe, predicts that if we trace the expansion backward, we reach a singularity. This is what we call the Big Bang. But again, physicists don't believe the singularity is real. Very close to time zero, quantum effects become important, and we need quantum gravity. Without that theory, we can't say what happened at the very beginning. We can say quite a lot about what happened shortly afterward. When the universe was about 1 second old, nuclear fusion occurred, creating hydrogen, helium, and trace amounts of other elements. The ratios we observe match beautifully with predictions, giving us confidence we understand the universe from at least 1 second onward. There's also a period called cosmic inflation that many cosmologists believe occurred in the first tiny fraction of a second. This rapid expansion would explain several puzzles about the universe, like why it's so uniform and flat. Inflation would have occurred when the universe was perhaps 10 to the minus 36 seconds old. But even inflation doesn't tell us about time zero itself. What happened at the very beginning? Can we even talk about the beginning of time? If time itself began with the Big Bang, then asking what happened before is like asking what's north of the North Pole. It's meaningless because there is no before. Some cosmologists have proposed models where the Big Bang isn't the absolute beginning. In cyclic models, the universe goes through repeated cycles. In eternal inflation models, inflation never completely ends, constantly creating new regions that undergo their own Big Bangs. These models are speculative. What we can say is that in extreme environments, our normal concepts of time break down. Near singularities, time might not be smooth and continuous. It might be discrete, or it might emerge from something more fundamental. The quest for quantum gravity and the nature of time. One of the great challenges in physics is reconciling quantum mechanics with general relativity. These two theories work extraordinarily well in their respective domains, but they seem fundamentally incompatible. When you try to apply quantum mechanics to gravity, to treat spacetime itself as a quantum system, you run into mathematical problems. Yet there are situations where both are important, like the center of a black hole or the very early universe. To understand these, we need a theory of quantum gravity. Several approaches have been proposed. The most famous is string theory, which proposes that fundamental constituents aren't particles but tiny, vibrating strings. Different vibration modes correspond to different particles. One mode would be the graviton, the quantum particle of gravity. String theory requires extra dimensions beyond the three we experience. What does string theory say about time? Time is treated much like in classical physics, as a parameter describing when things happen. However, some researchers have explored ideas where time might emerge from timeless quantum relationships. Loop quantum gravity takes a different path. It tries to quantize general relativity directly, treating space-time as composed of discrete, quantized units. Space isn't continuous but grainy at the tiniest scales. In some versions of loop quantum gravity, time emerges from timeless quantum relationships. The fundamental equations don't include time as a variable. Time, in this view, is not fundamental but emergent. This idea that time might not be fundamental is radical. We're used to thinking of time as the arena in which things happen. But if time is emergent, at the deepest level the universe might be described by timeless mathematics. How could time emerge from something timeless? One analogy is with temperature. Temperature is a macroscopic property, but it's not fundamental. At the microscopic level, there's just particles moving with different energies. Temperature emerges as a statistical property. Perhaps time is similar, emerging from some fundamental, timeless quantum state. This connects to the Wheeler-DeWitt equation, an attempt to apply quantum mechanics to the entire universe. The strange thing is it doesn't include time. This has led to the problem of time in quantum gravity. If the fundamental equation has no time, how do we explain that we experience time passing? These are deep questions at the frontier of physics. We don't have a complete theory of quantum gravity yet, so we don't know which approach is correct. But what's clear is that understanding time at the deepest level might require rethinking what time is entirely time travel. Physics, paradoxes, and possibilities. No exploration of time would be complete without addressing time travel. The idea captures the imagination, but what does physics actually say? Let's start with travel to the future, which is not only possible but actually happens. Remember time dilation from special relativity? If you travel at high speed, time passes more slowly for you than for people you left behind. When you return, you've aged less. You've effectively traveled to their future. This is completely real and has been measured. Astronauts on the International Space Station experience time dilation. After 6 months in orbit, an astronaut has aged about 0.005 seconds less than people on Earth. At higher speeds, the effect becomes dramatic. If you could travel at 99.995% the speed of light for 1 year, you'd return to find 100 years had passed on Earth. Gravity can also create time dilation. Near a black hole, time passes more slowly than far away. If you could orbit very close to a black hole's event horizon for what seems like a year, then escape, you might find that decades or centuries had passed outside. So future time travel is possible in principle. The challenge is purely technological. But what about traveling to the past? This is where things get complicated. Einstein's general relativity doesn't explicitly forbid past time travel. The equations allow solutions where time loops back on itself, called closed time-like curves. The most famous example was discovered by Kurt Gödel in 1949. Gödel found a solution describing a rotating universe where you could travel far enough to return to your starting point at an earlier time. Einstein was disturbed by this result. Other solutions with closed time-like curves have been found. Rotating black holes might contain them. Traversable wormholes could potentially be manipulated to create time machines. But there are enormous obstacles. First, we don't know if wormholes can exist. They require exotic matter with negative energy density. Second, they might be unstable. Third, quantum effects might prevent time machines from functioning. Stephen Hawking proposed the chronology protection conjecture. The laws of physics prevent time travel to the past, protecting the universe from paradoxes. Quantum effects might create infinite energy densities that destroy the time machine before it could function. This brings us to paradoxes. The most famous is the grandfather paradox. If you travel back and prevent your grandfather from meeting your grandmother, you wouldn't be born. But if you're not born, you can't travel back. It's an infinite loop of contradiction. There are proposed resolutions. One is the consistency conjecture. Time travel is possible, but you can't change the past. If you try to prevent your grandfather from meeting your grandmother, you'll fail. The timeline is consistent. It just includes your time travel. Another resolution is the many worlds interpretation. If you travel back and change something, you create a new branch, a parallel timeline. Each timeline is consistent internally, but you can never return to your original timeline. A third possibility is that time travel to the past is simply impossible, that the laws of physics prevent it despite apparent solutions in general relativity. Perhaps quantum gravity will rule out closed time-like curves. Most physicists lean toward this view. While we can't rule out time travel to the past with certainty, it seems unlikely. Nature appears to protect causality, to prevent the kinds of paradoxes that backward time travel would create. What we can say with confidence is that forward time travel is real and has been observed. Backward time travel remains speculative, probably impossible, but not yet definitively ruled out. Cultural and philosophical perspectives on time. While science investigates time's physical nature, human cultures have developed diverse ways of thinking about time. These perspectives remind us that our relationship with time is not just scientific but deeply cultural and personal. In many Western philosophical traditions, time has often been viewed as linear, flowing from past through present to future. This linear view has roots in Judeo-Christian theology, which sees history as having a beginning and moving toward an ultimate end. Events happen once and are unique. This influenced Western science and the idea of progress. But not all cultures view time this way. Many ancient and indigenous cultures have conceived of time as cyclical, repeating in patterns like the seasons. In Hindu and Buddhist traditions, time is often understood as cyclical on grand scales. The universe goes through vast cycles of creation and destruction in Hindu cosmology. These cycles are called kalpa. Each kalpa lasts about 8 billion years. The universe is created, exists, and then is destroyed, only to be created again in an endless cycle. These cyclical views don't see history as progressing toward a goal but as repeating eternal patterns. Ancient Greek philosophy included both cyclical and linear elements. The Stoics believed in eternal recurrence, the idea that the universe periodically returns to exactly the same state and repeats identically forever. Nietzsche took up this idea in the 19th century, asking, if you had to live your life over infinitely many times, would you embrace it or despair? Different cultures also have different relationships with punctuality and scheduling. In many Western industrialized societies, time is treated as a scarce resource to be managed and optimized. This has been called monochronic time, where tasks are done sequentially according to schedule. In contrast, some cultures practice polychronic time, where activities are scheduled more flexibly around events and relationships rather than the clock. Multiple things might happen simultaneously. This doesn't mean less efficiency, just different priorities. Language also shapes how we think about time. Many languages use spatial metaphors. In English, events are ahead or behind us, the future forward and the past backward. But the Aymara language reverses this, with the past in front because it's known and visible, and the future behind because it's unknown. Philosophy has also grappled with time in ways beyond science. The existentialist philosophers, particularly Martin Heidegger, placed time at the center of human existence. Heidegger argued that our awareness of our own mortality is fundamental to what it means to be human. We exist as beings oriented toward the future while being shaped by our past. Henri Bergson, a French philosopher, distinguished between clock time, the measured time of physics, and lived time, the qualitative experience of duration. Bergson argued that science, by spatializing time into discrete units, misses something essential about time's nature as experienced. A minute of boredom feels different from a minute of excitement, even though both are 60 seconds. These philosophical perspectives remind us that time is not just a topic for physics but something deeply woven into human life and consciousness. How we think about time shapes how we live, what we value, and how we understand ourselves. Time, aging, and the cosmic calendar. One of the most personal aspects of time is aging. The way time leaves its mark on our bodies and minds. We all experience the passage of time through the accumulation of years, the changes in our capabilities, the gradual accumulation of experiences. Biological aging is a complex process, not yet fully understood. At the cellular level, aging involves accumulation of damage to DNA and proteins. Cells have repair mechanisms, but these become less efficient over time. Telomeres, protective caps on chromosomes, shorten with each cell division. Mitochondria accumulate damage and become less efficient. All these processes are influenced by genetics, but also by lifestyle. The rate of aging varies considerably between individuals. Some age slowly, remaining vigorous into their 80s and 90s. Others age more rapidly. Is aging inevitable? From a physical perspective, the second law of thermodynamics suggests yes. Maintaining a low-entropy state like a living organism requires constant energy input. Eventually, the mechanisms that maintain order break down. But some organisms age very slowly. Certain tortoises can live over 150 years. Bowhead whales can live over 200 years. Some trees live for thousands of years. Bristlecone pines in California include individuals over 5,000 years old. Some researchers are trying to slow or reverse aging. Caloric restriction has been shown to extend lifespan in many organisms. Certain drugs have shown promise in animal models. But even if we could dramatically extend human lifespan, we'd still be bound by time. Our human lifespan, typically 7 to 9 decades, gives us a particular perspective on time. To put this in cosmic perspective, imagine compressing the entire history of the universe into a single calendar year. This is the cosmic calendar. On this scale, the Big Bang happens at the first second of January 1st. The Milky Way forms around March. Our solar system doesn't form until early September. Earth coalesces on September 6th or 7th. The earliest life appears around September 21st. Complex multicellular life doesn't appear until mid-November. The Cambrian explosion happens around December 17th. Dinosaurs appear on December 25th and go extinct on December 30th. The entire age of dinosaurs is just 5 days. Humans, Homo sapiens, appear at about 10:30 p.m. on December 31st. All of recorded human history occupies the last few seconds before midnight. The entire modern era is less than 1 second. An average human lifespan is about 1/7 of 1 second on the cosmic calendar. From the universe's perspective, our lives are briefer than the blink of an eye. Everything humanity has ever done has happened in the last 10 seconds of the cosmic year. This perspective can be humbling, even vertiginous. But it can also be inspiring. In those last 10 seconds, we've gone from hunter-gatherers to a global civilization. We've developed science and technology. We've begun to understand the universe itself. Against this vast cosmic backdrop, human time seems infinitesimally small. Yet it's the only time we have, the only time we can experience. And within our limited span, we can still find meaning, create beauty, love and learn and grow. Time's vastness doesn't diminish the significance of the time we have. If anything, it makes each moment more precious. Measuring time with modern precision, we began with ancient sundials and water clocks. Let's come full circle and look at how we measure time today, with precision that would have seemed like magic to ancient astronomers. The story of increasingly accurate timekeeping is closely connected with navigation. In the 18th century, determining longitude at sea was a major problem. Latitude is easy to measure by observing the sun or stars, but longitude requires knowing the time difference between your current location and a reference point. The problem was that mechanical clocks weren't accurate enough. Temperature changes, the rocking of ships, all these affected timekeeping. In 1714, the British government offered the Longitude Prize. It was eventually won by John Harrison, who spent decades developing marine chronometers. Harrison's fourth chronometer, H4, completed in 1759, was about the size of a large pocket watch. On a voyage to Jamaica in 1761, it lost only 5 seconds over 81 days. This made accurate navigation possible, transforming seafaring and global trade. Meanwhile, timekeeping on land improved. Pendulum clocks achieved accuracies of a few hundredths of a second per day by the 19th century. The 20th century brought revolutionary improvements. Quartz crystal clocks, developed in the 1920s, used the vibrations of a quartz crystal to keep time. Quartz crystals vibrate at very stable frequencies when an electric current is applied. Quartz clocks achieved accuracies of about 1/1000th of a second per day. But even quartz clocks are crude compared to atomic clocks, which use the vibrations of atoms themselves. The first atomic clock was built in 1949. The breakthrough came with cesium atomic clocks. Modern cesium atomic clocks count oscillations at 9,192,631,770 cycles per second. That's the definition of 1 second, the duration of that many periods of radiation from the cesium-133 atom. The best cesium fountain atomic clocks achieve accuracies of about 1 second in 30 million years. But even these are being surpassed. Optical atomic clocks, which use transitions at higher frequencies, have achieved accuracies of about 1 second in 15 billion years, longer than the current age of the universe. These clocks are so precise they can detect gravitational time dilation from being raised just a centimeter higher. Einstein's relativity isn't just exotic physics. These clocks measure relativistic effects from everyday changes in height. Why do we need such precise clocks? One reason is fundamental science. Testing relativity, probing quantum mechanics, searching for variations in fundamental constants, all require the best clocks we can build. Atomic clocks on GPS satellites need to account for relativity. High-speed financial trading, telecommunications networks, power grids, all rely on precise timing. And there's the simple human drive to measure things as accurately as possible, to push the boundaries. We've come from sundials to measuring time in billionths of a second, from errors of minutes per day to stability over billions of years. This journey reflects our deeper quest to understand time itself. The better we can measure time, the better we can test our theories about its nature. As our clocks improve, they open new windows into physics. Perhaps future clocks will detect gravitational waves directly, or probe the quantum structure of space-time, or discover new physics we haven't imagined. Time in art, music, and human experience beyond science and philosophy. Time finds expression in art, music, and literature, reflecting its deep significance in human experience. Artists have long been fascinated by time's passage and mysteries. In visual art, time presents a unique challenge. Painting and sculpture are static, frozen moments. Yet artists have found ways to evoke time's flow. Impressionist painters like Claude Monet created series showing the same scene at different times of day or seasons. Monet's haystacks and water lilies show how light and atmosphere change with time. Futurist artists tried to depict motion and time directly. Marcel Duchamp's nude descending a staircase shows a figure as overlapping images, as if multiple moments are superimposed. Salvador Dali's The Persistence of Memory features melting clocks suggesting time becoming fluid, losing its rigid structure. Photography and film have a different relationship with time. A photograph freezes a moment perfectly. Early commentators noted this uncanny quality. A photograph shows exactly how things looked at a particular instant, but that instant is gone forever. Film captures time itself. 24 frames per second, each a frozen moment, played back to recreate motion. Film can manipulate time, slowing it down, speeding it up, jumping forward or backward. Directors like Andrei Tarkovsky used long, contemplative shots to make viewers intensely aware of time passing. Music is often called the temporal art because it exists only in time. Unlike a painting you can look at all at once, music must unfold moment by moment. A melody is a pattern in time. Rhythm is the organization of time into regular beats. Composers have explored time in fascinating ways. In minimalist music, like Steve Reich's compositions, simple patterns repeat with gradual changes, creating a sense of time stretching out. In John Cage's 4 minutes 33 seconds, the performer sits silently. The piece is the time itself, the ambient sounds of the concert hall. Literature is also a temporal medium. You read a book over time, and the order in which information is revealed shapes your experience. Some novels make time itself a central theme, like Proust's In Search of Lost Time, exploring how memory works, how the past persists in the present. Poetry often tries to capture moments intensely, to freeze time in language. The haiku tradition creates tiny, perfect snapshots of moments. Other poems confront time's passage directly, like Shakespeare's sonnets about aging and mortality. Time is also central to human ritual and celebration. Birthdays mark the passage of years. Anniversaries commemorate past events. New Year's celebrations acknowledge the transition, recognizing time's flow. Seasonal celebrations connect human time to cosmic time, to the Earth's orbit. Spring festivals celebrate renewal. Harvest festivals mark abundance. The way we celebrate time reveals what we value. We mark beginnings and endings, transitions and milestones. Graduations, weddings, retirements. These are moments when we pause to acknowledge that something has changed, that we're moving from one phase to another. Grief is deeply connected to time. When someone dies, we mourn not just their absence but the end of shared time, the future moments we won't have. Grief is often described as a process that takes time. Memory connects us to the past, to times we've experienced but that no longer exist except in our minds. We preserve memories through photographs, videos, written accounts, trying to hold on to time that slipped away. Nostalgia is a bittersweet emotion, a longing for the past, for earlier times that seem simpler or happier. Hope and anticipation are future-oriented emotions. We plan, we dream, we worry about what's to come. This future orientation is uniquely human. We can imagine possibilities, make predictions, work toward distant goals. Time in human experience is never just an abstract parameter. It's the fabric of our lives, the medium in which our stories unfold. We say we don't have enough time, or we're killing time, or time flew by. These metaphors reveal how deeply time shapes our thinking. Time is money, something to be spent. Time is a river, carrying us along. Time is a thief, stealing our youth. Time is a healer, easing pain. Bringing it all together. What is time? We've journeyed through physics and philosophy, through ancient sundials and atomic clocks, through black holes and the Big Bang, through consciousness and culture. We've seen time from many angles. So, after all this exploration, can we finally answer, what is time? The honest answer is that we still don't fully know. Time remains one of the deepest mysteries in science and philosophy, but our exploration has revealed many fascinating aspects. We know that time is not absolute and universal as Newton thought. Einstein showed us that time is relative, passing at different rates for different observers depending on their motion and position in gravitational fields. Time is not separate from space but unified into four-dimensional space-time. The present moment is not universal but depends on your reference frame. We know that time has a direction, an arrow pointing from past to future, and that this arrow arises from entropy. The universe began in a special, low-entropy state and has been increasing entropy ever since. We remember the past and not the future. Causes precede effects. Eggs break but don't unbreak, all because of entropy. We know that at the quantum level, time behaves strangely. Measurement processes seem irreversible. There are tiny violations of time reversal symmetry in certain particle interactions. The future is not determined by the past because quantum mechanics introduces fundamental randomness. We suspect that time might not be fundamental at the deepest level. In quantum gravity, time might emerge from something more basic. This is speculative, but it's a direction current research explores. We know that our conscious experience of time, the feeling of time flowing, is real and important even if it doesn't straightforwardly map onto the time of physics. The relationship between experimental time and physical time is a mystery we're still unraveling. We know that different cultures conceptualize time differently, some seeing it as linear and progressive, others as cyclical. We know that language shapes how we think about time, that art and music explore it in unique ways, that rituals mark time's passage. But beyond all this knowledge, there's still mystery. Why does time exist at all? Why does the universe have a temporal dimension? What really happens at the beginning of time in the Big Bang, or at the end of time in a black hole? Is time truly fundamental, or does it emerge from something else? These questions remain open. Physics is still developing, still probing deeper. Theories of quantum gravity might revolutionize our understanding just as relativity did. Philosophy continues to grapple with the relationship between physical time and experience time. What we can say is that time is fascinating, multifaceted, and essential to everything we know and experience. It's the dimension in which change occurs, in which events unfold. It's the medium of our lives, the framework within which we exist. Time is what prevents everything from happening at once. Without time, there would be no change, no motion, no causality, no life. The universe would be eternally static. Time is what makes the universe dynamic, what allows for novelty and creativity, what makes possible the evolution of stars and galaxies and life and consciousness. And time is personal. Each of us has a limited amount of it, a finite span between birth and death. How we use our time shapes who we become and what we contribute to the world. Time is the most valuable resource we have because it's the one we can never get more of. So perhaps the deepest answer to what is time is simply this. Time is the fundamental structure of change and existence, both in the universe at large and in our individual lives. It's something we measure with clocks but experience with consciousness, something we study with physics but understand through living. Time is the great mystery that science probes and philosophy ponders, yet that each of us navigates every day simply by being alive. A gentle conclusion: we've reached the end of our exploration into the nature of time, though in a sense, the exploration never truly ends. Time continues to fascinate scientists and philosophers, continues to inspire artists and musicians, continues to puzzle anyone who stops to think about it seriously. You've learned tonight about sundials and water clocks, about Einstein's relativity and the flexibility of time, about entropy and the arrow of time, about quantum mechanics and measurement, about black holes and the Big Bang, about consciousness and culture, about atomic clocks and the cosmic calendar, about art and ritual and human experience. You've seen time from many perspectives, each revealing something different about its nature. The beautiful thing about learning about time is that it changes how you experience it. When you understand that time is relative, that the present moment is not universal, the world becomes a bit stranger and more wonderful. When you understand entropy and the arrow of time, you see the one-way flow of events as something profound rather than merely obvious. When you understand how brief human existence is on the cosmic calendar, each moment becomes more precious. Time will continue its flow, entropy will continue increasing, the universe will continue expanding. Tomorrow will come, as it always does, carrying you forward into your future. But hopefully, you'll greet that tomorrow with a deeper appreciation for the mystery and wonder of time itself. Thank you for spending this time with me, for allowing me to guide you through these ideas and discoveries. If you enjoyed this gentle exploration of time's mysteries, I hope you'll return for more calm learning. There are so many other fascinating topics to explore, so many other mysteries to gently unpack before sleep. Until next time, rest well, and may your dreams carry you peacefully through the hours until morning comes again. Time continues, as it always has, as it always will, carrying us forward moment by moment into whatever comes next. And that, perhaps, is both the simplest and most profound thing we can say about time. Good night, and thank you for listening. Subscribe when you wake up. Sleep well. See you soon.